I have so many nightmares in which I'm speaking the wrong language to people, and I see that it's based on real life. I apologize. So thank you again to everybody for staying around. Apologize again for the coffee. It will hopefully be ready after this talk. One more thing. Like I said, please try not to lose your name tag because we will need this to get in on Wednesday to the Museo de la Luz. And if you're going tomorrow on the excursion, if you're going to the banquet and you have not yet responded to the email about which type of food, vegetarian, beef, or tuna, please respond to that Google form email because we need to tell the hacienda where we are going as soon as possible what everyone will be ordering. So with that housekeeping out of the way, I'd like to thank David Damanik for coming, and he will be talking to us about Return to Wonderland. So I'll be interested to see how maybe this is related to Alice in Wonderland.
Well,
is that the analogy being made?
Yes, no.
Okay,
We'll see.
We
shall see. Yeah, so thank you very much for the introduction. I'd like to thank all the organizers for the work they put into organizing this wonderful conference. Thank you for having me, and happy belated birthday to Volker. So it's a pleasure to actually meet you in person finally, right? I don't know if we've met before. There you go. So wonderful. Okay, so yes, I will talk about the return to Wonderland, and I think the immediate connection will be to Mary Simon's Wonderland theorem. And so we want to return to that. And this worked before. Okay, do I have to point somewhere? No. So it did work before. Oh. Okay. There you go. Okay, so I will talk about two works that are both joined with Otto Avila, who's at University of Zurich, and Impa in Rio de Janeiro. So the two works shed different lights on the Wonderland theorem, but they are both closely connected to it, and I'll try to explain what these connections are. And so for each of these two works, I will give a non-technical explanation of what happens and some idea of what's going on. But the proofs are such that I won't present them here. And so as a very mild excuse, I will give you a proof here, basically because the Bach category theorem is so useful in this context. And once you see the proof, you see in some sense, it's almost a triviality. It's just, I mean, it's a statement that proves itself when you think about it. So, sorry, okay. Right, so the Bach category theorem says that if you have a complete metric space, and then you have a countable collection of subsets of that space, each of which is dense and open. So that's your starting point. And then if you intersect them all, then this intersection is dense. So that's what it says. And so just in general, the terminology is such that a countable intersection of open subsets is referred to as a G delta set. And so this really means that a dense G delta set is really nothing but the countable intersection of dense open sets. It's really the same thing. And so as I said, it's a statement that proves itself. So you really just write down what you want, and then you try to work with what you have. Okay, so you start with a complete metric space, and you have a countable collection of dense open sets. So the claim is that their intersection is dense. So at the very end, I want to claim that the intersection of these guys is dense. So that's my goal. In order to do that, you start with a point, an epsilon ball around it, and you want to find a point in the epsilon neighborhood that belongs to the intersection. That's your goal. Okay, so let's try to do that. So you start with this initial radius that's given to you. And so you stare at the following line. So you have this V naught and this radius epsilon around it. So this is an open ball. O1 is open, so this is an open set. And also, because O1 is dense, there will be a point in this open set. And because it's open, you can fit a ball around it. And if you make the radius a little smaller, you can fit the closed ball inside there, right? So this is really a direct consequence of O1 being open and dense, and this here open. So you can fit a closed ball inside this intersection. And that's basically the whole proof, because all you do is you iterate that. So this is the same statement with k increased by 1. Okay, it's the exact same statement. And so, of course, in this construction, you can ensure that these radii go to 0. If they don't, then you take them, half them every time you want. And so then, then you have the sequence going to 0. By this construction, so this guy is contained in this, and of course, therefore, in the closure of it. So you have a nested sequence of closed balls. Because your metric space is complete, they will shrink down to a point. So the radii go to 0, the space is complete, so they shrink down to a point. And so this point, that's basically the intersection of this nested sequence of closed balls with radii going to 0, must belong to all of them. Okay, but if it belongs to all of them, it belongs to each of these, but in particular each of these. Okay, so this point that belongs to all these balls actually belongs to all the OKs, and that's it. Okay, so that's what I was trying to show, that the intersection of the OKs is dense in D. Okay, so it's really a statement that proves itself once you write down what you have and what you are aiming for. Okay, so the magic of Baire is that you can basically force properties to occur simultaneously if each of them happens, on a dense G delta set. So really, the most important consequence of the statement is if you take a countable intersection of dense open sets and another countable intersection of dense open sets, intersecting them is a countable intersection of dense open sets. Okay, but they may describe different properties, And so if each of them is, so the terminology is generic, then their intersection is. And so this really underlies the original Wonderland theorem, which I will explain. So this is Simon's Wonderland theorem, I think it was published in 95. It's actually, the funny thing is, so I think I was sort of just about to start my PhD studies. No one told me what I should be looking at, so I first didn't know what to look at. But then Barry Simon and his friends posted preprints. Okay, so they all were released in the mid-90s. It was a series of 7 papers, and they were all about singular continuous spectrum. And so this here is from the first of these 7 papers, and basically the message is, if you just condense it to one sentence, that one sentence is singular continuous spectrum is generic. Some of you may have heard that sentence, and that's really what this first paper in the series of 7 embodies. And the reason why singular continuous spectrum is generic is there. Okay, so at the time, I mean, it was a surprising result because there were many results about, so this is in the context of Schrödinger operators, by the way. So there were many Schrödinger operators with some absolutely continuous spectrum, Schrödinger operators with some few-point spectrum. Okay, so there were some artificial examples with single continuous spectrum, but not sort of, to the degree that this result would actually exhibit. And so, okay, so I will give you the punchline in a moment. But the point is that you knew some few-point spectrum examples, and you knew some absolutely continuous spectrum examples. But for some reason, there tells you much more. And so that's what I want to explain. So let me first actually state the theorem. So the Wonderland theorem takes many guises, but let me actually look at this particular very simple version. So let's look at, so you don't have to, but let's do it for now. Let's look at discrete Schrödinger operators on the line. So the Hilbert space is little r2 of z. I look at bounded potentials v from z to r. And so the theorem is the following. So the important thing to keep in mind is that it's a topological statement. Okay, so we are really talking about something that happens on a set that's described via its topology, namely the countable intersection of dense open sets. And so in some sense, you need a topology on your space of potentials. Okay, so for this instance of the Wonderland theorem, what you do is you take a compact interval of length 2r, where r really is an upper bound on the L infinity norm of your potential. And so then you take this interval to the power z, so all maps from z into minus rr, and that, written in this form, obviously is a product space. You put the standard topology on the interval, and then the product topology on the product space. And then you think a little bit, and yes, it's a complete metric space. Okay, so there in principle applies. And so let's ask whether this set is large in any sense. And what's the set? Okay, so you look at the potentials. The Laplace is fixed anyway, so all you do is vary the potential here. As you vary the potential, you ask yourself whether the operator is purely singular continuous spectrum. It's a question that you may ask. The question is that a phenomenon that occurs often? But then, of course, you have to specify the sense in which it often actually is meant. And so here the sense of often is the sense of topological genericity. So the claim is, and actually what the theorem says, is that this set of V's is a density delta C. So that's what the theorem is. And so in that sense, singular continuous spectrum is generic. Okay, so now I'm again hinting at sort of the punchline, which I'll explain in more detail, I think, on the next slide. So what I find shocking about this proof, and I think it's really unique in that regard, I can't really think of another example. So you want to show that something happens, in this case, singular continuous spectrum. In fact, you want to show that it happens very often. But anyway, you want to show that singular continuous spectrum occurs. All you have to do in the proof is to show that pure point spectrum occurs and absolutely continuous spectrum occurs. That's all you have to do. And that's it. That's the end of the proof. It sounds absolutely insane, but it's actually true. So I will explain that on the next slide. Okay, so that's the other thing I already hinted at. So there were sparse potentials constructed by Pearson. So, I mean, it was known that singular continuous spectrum can occur. But again, those examples at the time were considered artificial, whereas the genericity result sort of tells you, okay, it really happens a lot and you should take it seriously, and it's everywhere. Okay, so there was a series of several papers which I've mentioned. This is part one. And so all of these papers talked about how singular continuous spectrum can arise in families and what to do when you have it. Okay, so here's the slide that actually makes concrete what I've alluded to twice already. So here's how the theorem actually is proven. So this paper from 95, it did appear in the annals because it really was absolutely new realization, led to a paradigm shift. But the mathematical content was limited. I don't know if Barry will agree, but there's really not much going on. So the mathematical content is in items 1 and 2. So basically what Barry had to do is he had to describe, one, the set of V's for which the operator has singular spectrum as a G delta set. Not the word dense, just a G delta set. A G delta set is a countable intersection of open sets. So you need to somehow write down countably many conditions that are open. If you intersect them all, that must be equivalent to having a singular spectrum. Well, he did that. Item number 2 is to do the same thing for a continuous spectrum. Okay, you look at the potentials V so that the associated Schrödinger operator has purely continuous spectrum. Again, Barry found a description of the set using countably many open conditions. Okay, so now you have 2 G delta sets. Again, the word dense hasn't appeared yet. So here comes the shocking aspect of this whole proof. Once you know that these guys are G deltas, you somehow have to sneak in this information about something being dense. And so actually, let me start with 4, ignore 3 for a second, because 4 is easier, I should have switched them. So look at the V's that are periodic. A periodic sequence is really one that repeats finitely many values periodically. So that's a periodic sequence. It's been known forever that if you take a periodic potential, that the associated Schrödinger operator has purely absolutely continuous spectrum. Okay, now 2 important things. One, well, this set here, the periodic V's, is dense in minus RR to the Z. Okay, so now you have to think about how the product topology is generated. It's generated by a metric, and the metric places more emphasis on what's close to the origin and much less on what's far away. So you can just approximate any potential by cutting out a centered piece and letting the radius go to infinity. Right? You cut out the piece, repeat it periodically, and then make the piece larger. That gives you periodic approximation of anything you start out with. So this shows you that this set is dense. But, well, the operators have purely absolutely continuous spectrum, and so in particular, they have continuous spectrum. But the continuous spectrum is G delta, and this set is dense. So this set here has a dense subset. Being a G delta means it is a dense G delta. Okay? And so now we go to 3. As I said, it's a little harder to prove this. This has been known for a long time that this leads to AC spectrum, but this is a result from the 80s. Okay, so you can take random potentials in 1 dimension. It's been known since the 80s, well, for certain distributions, that's good enough for this application, that the associated Schrödinger operator is almost surely a few-point spectrum. And this full measure set of random realizations of V also is dense in the sequence space. Yes.
I have a very silly question. What does it mean for V to be random?
Yeah. Okay, so what you do is you put a uniform measure on this interval, okay, just density 1/2R uniformly. And then you draw, according to that measure, a value from that interval. That gives you your potential value at one side. And now you do that at all sides with the same distribution independently. That generates a 2-sided random sequence, okay, according to this product measure, so the back measure to the Z. And then almost every element with respect to this product measure has a Schrödinger operator that has pure point spectrum. And again, this full measure set is actually dense in the sequence space because you took a fully supported measure.
Okay, thank you.
And now you argue in the same way. I already said this set of random realizations for which you know you have pure point spectrum is dense. But of course, if you have pure point spectrum, you're singular. But singular spectrum is a G delta. And again, so it's a dense subset of a G delta set, meaning that the bigger set is a dense G delta. Okay, so what you see here is, except for these 2 descriptions as G delta sets, which is what Barry did in this paper, everything else comes down to showing that pure point spectrum appears densely, and absolutely continuous spectrum appears densely. And now the genius idea is to reinterpret AC spectrum as continuous spectrum and pure point spectrum as singular spectrum, because those two more general properties are the delta properties. And then you can intersect them. Okay, so you have point spectrum, you have AC spectrum. If you intersect those, you get nothing because they are incompatible. If you enlarge both classes and then you intersect, but really when you intersect them, you get rid of the pure point nature and the AC nature, and you're left with singular continuous spectrum. So it's really a very, very nice proof. But again, it's a short proof, and all the work is basically here. So this really is easy to prove. This requires some work, but even that is by now very well understood. And so this is how the genericity of singular continuous spectrum arises in this context. Okay, there you go. So I want to talk about these two results with Otto Avila. And the first one is about a result that's in the spirit of the Wonderland theorem. And so the result concerns families, ergodic families of Schrödinger operators. And so let me fix a setting, which I'll later generalize. But for now, let me fix the following setting. And I'll tell you in a moment why I'm interested in this setting. So you take a compact metric space omega, and then you take a homeomorphism T from omega to omega. Okay, and so now what you can do is you can put you can put the Borel sigma on omega, and you could look at Borel probability measures on omega. And if you have a measure on omega, you can push it forward under T. Okay, you just push the measure forward, and you can ask whether the push forward measure is the same as before. That's an invariant measure. Okay, and usually we have a bunch of invariant measures, and the extremal points are the ergodic measures. But really, what they mean. So I'm assuming that mu is an ergodic measure. That means if you have a set that's invariant under T, that must mean that the set has weight 0 or 1 with respect to that measure, then it's ergodic. So it's an indecomposability result. And so, like I said, the extremal points of the invariant measures are ergodic, precisely. And so in particular, and also you can always find at least one invariant measure, so therefore at least one ergodic measure. Anyway, so there are ergodic measures and you fix one. So you fix a compact metric space, a homeomorphism, and a T ergodic Borel probability measure. Okay, so you fix that. It's called the base dynamical system. And now you want to generate Schrödinger operators. So right now, if you iterate this homeomorphism, you can generate two-sided sequences in omega. That's not a Schrödinger operator yet. So in order to generate a Schrödinger operator, you need to generate a potential. We're in the discrete setting, so you need a two-sided real-valued sequence. You have a sequence in omega, so you can turn that into a real-valued sequence with a function that maps you from omega to r. That's what we call a sampling function. So you sample this process. Okay, so then, of course, if you apply this real-valued function to your T orbit of a little omega and capital omega, you do get a two-sided real-valued sequence that you can use as a potential, and I do so. Here's your potential, here's your discrete Laplacian, here's your operator in L2 of Z. Note that it depends on this initial point here. So this actually is an operator that should be indexed by this little omega. And so as omega runs through the space capital omega, you get a whole family of operators. Why did I want this measure mu to be ergodic? Well, the whole point of ergodicity is the existence of ergodic theorems. And so if you have something that's ergodic, well, one characterization of being ergodic is that invariant functions are almost really constant. And so what does invariant actually mean? Well, if you apply T to omega, then, well, if you replace omega by T omega, you're really dealing with T to the n plus 1 omega, which in this potential just shifts the potential one side over. That's all that happens when you pass from omega to T omega. So mapping omega to T omega shifts the potential, which is a unitary transformation in Hilbert space, doesn't change the spectrum. Okay, so if you shift the potential, the spectrum stays the same. And so ergodicity means if something is T invariant, it's almost really constant. And so this already should convince you that the spectrum of this operator should be mu almost really constant. That's true, and that's how it's proved. Okay, so this almost sure spectrum is denoted by sigma. It's the spectrum of H omega for mu almost every little omega. And you can run the same game with a little more work for the two-point spectrum, singular continuous spectrum, and AC spectrum. Okay, so all these partial spectra are also mu almost surely constant. Okay, so now I've generated a framework. I should explain why I care. So, I mean, the primary reason to introduce this framework is because it encompasses examples that people care about. So, in the previous slide, we looked at periodic potentials and random potentials. Both of these classes can be viewed as ergodic potentials. On top of that, you can view almost periodic potentials and many other classes as ergodic potentials. For some reason, each of them generates some ergodic measure on some compact metric space. So it's really the main reason to study this more general class, because you can see which common features of the various example classes are really the consequences of just being ergodic. Okay, so for example, this almost sure constancy of spectra is really an immediate consequence of ergodicity, but that was the first result people proved about random potentials and almost periodic potentials. And many other things are really more naturally handled in this more general setting. Okay, so commercial break. So if you ever find yourself in a situation where you want to learn more about ergodic Schrödinger operators, there are books for that. You can read those books. Okay, so that's end of the commercial break. Okay, so you can already see where this is going. This makes it sound like a one-to-one theorem. And to set things up, let me recall an old result. I mean, old is relative, but it's relatively old. So it's from 20 years ago. So in the setting that I specified, we want to assume that mu has no atoms. There is no single point in omega that has positive weight with respect to our measure. I'll explain in a second why this is a natural assumption. So there is an assumption here, but that's it. Except for this one assumption, it's really a result that applies to all these families, or rather to all base dynamics, because what happens here is you're varying the sampling function. This is the function that turns sequences in omega into sequences with values in R. Okay, so you fix a base dynamical system omega t mu, and then you vary f and ask what happens to these almost sure spectra, in this case, the almost sure AC spectrum. And the result is, well, if you're interested in the absence of AC spectrum almost surely, this will happen for a density delta set of sampling functions. That's the result. Okay, and so let me now comment on the assumption. So what does, why do I assume that mu is non-atomic? So assume mu has an atom. There's a point with positive weight. Remember that the measure is invariant. So if I take a point with positive weight and map it over by t, its image must have the same weight because the measure is invariant. And then I keep going. But the whole measure is a probability measure. So if I start with a positive weight that keeps reproducing along the orbit, and the whole measure is finite, the orbit must close. It can't be infinitely many distinct points that all have the same positive weight. Okay, so now you have this orbit that must close. All the points have the same weight. But then it's also ergodic, meaning decomposable. So I can't decompose a space into something that has positive weight and whose complement also has positive weight. So because of that, this closed orbit must have all the weight. Okay, so therefore, if you have the situation where there is an atom, then you're really dealing with a periodic case. So mu almost every omega will be such that H omega is periodic, but that of course means that it has AC spectrum. So you cannot prove absence of AC spectrum if there is an atom. So you need to assume that you have no atoms. And as soon as you do assume that you have no atoms, the result holds. So this is a genericity statement, but it does concern the absence of AC spectrum. Okay, so okay, I think so. This is what I just explained. Okay, and so here you can ignore this, but for those who care, I mean, there's a reason that Adil and I work on these things. So he comes from dynamical systems, I come from Schrödinger operators, and so we collaborate because we prove results about Schrödinger operators using methods from dynamical systems. So it's a very natural collaboration. And there's a reformulation of this result which is more attractive to people in dynamics. So there is a quantity called the Lyapunov exponent. And so Lyapunov exponents being positive is a generalization of so-called uniformly hyperbolic behavior. And so the non-uniform version of hyperbolic behavior is something that's of interest to the analysis. It's just a fact. And so the reformulation here of this theorem is that for density delta of f's, you have a one-parameter family of dynamical systems, and then for almost all values of the parameters, the Lyapunov exponent is positive. That's the reformulation of the result. It's equivalent, the Ekotani theory, but if you care about the Lyapunov exponents, the other formulation may be more attractive. But you can ignore this if you want. Okay, sorry. Okay. So, generically, the almost sure absolutely continuous spectrum is empty. So, of course, I've set things up that I'm sort of forcing you to already ask the next question. Well, if the absence of AC spectrum is generic, what about the absence of point spectrum? If that was generic, I could again intersect these two Benchy delta sets. And what I would get is that generically I have almost surely purely singular continuous spectrum. So the previous result was proved 20 years ago. Of course, it's not like we didn't ask the question over this 20-year span. The question has been around, but it wasn't clear what to do. But we can prove it now. Okay, so this plus means it's not published yet. It's not even on the archive, but the preprint exists and has been circulated. But anyway, so the result is exactly what you hope might be true. So the set of sampling functions for which the almost sure point spectrum is empty is also a density delta set. Okay, so of course now you can intersect the two density delta sets, and you get on a density delta set that you have purely singular continuous spectrum almost surely. Okay, so good question, and the answer is no. Exactly. So this is actually something that will be explicit on this slide. Exactly. So this theorem has no assumptions. It's just always true. And there's another very nice aspect which I'll also make explicit. But first, maybe as a downer, this really is a difficult result because there were no methods. I mean, that's really the reason why there was no progress over 20 years. It's absolutely not clear what to do. So luckily, there is now some insight into what one ought to be doing, and I'll try to explain that in the talk. Okay. So, so this theorem is surprisingly general. So once you actually see a way forward, it produces a result which is really nice. So for one thing, to answer Volker's question, no, there's absolutely no assumption on the base dynamics needed, so that's good. But much more importantly, now I really should generalize to higher dimensions. So the reason why I sort of did mention this equivalent formulation in terms of positive Lyapunov exponents for almost all energies is to really make explicit that we're talking about something that can be reformulated. Okay, so for those of you who are not into dynamics but into one-dimensional Schrödinger operators, in terms of transfer matrices. So one-dimensional Schrödinger operators are studied in terms of transfer matrices. In this situation where the potentials are dynamically generated, the transfer matrices are also dynamically generated. And it's for those dynamical systems that we prove positive Lyapunov exponents. Okay, so that's of course a big difference between one-dimensional Schrödinger operators and higher-dimensional Schrödinger operators because, well, the solution space in one dimension is finite dimensional, and it's not finite dimensional higher dimension, so there is no formulation in terms of finite dimensional transfer matrices. It just isn't. Okay, but this theorem doesn't rely on transfer matrices at all. And therefore, one could ask if it holds in higher dimensions, and the answer is yes, it does. So here's the higher dimensional version. So it's almost the same. Everything looks entirely the same. The only difference is that before we had a single homeomorphism, which we can iterate in forward and backward time, so it's a Z action. So if you have a ZD action by homeomorphisms, you can, in the exact same way, define Schrödinger operators in L2 of ZD. Everything else is the same. So even the definition of the potential is the same. It's just that now this M is in ZD, but everything else is the same. So you put the d-dimensional Laplacian here, you put this dynamically generated potential here, and now you have a family H omega. The ergodicity assumption is still here, and you still have these almost sure spectrum and the almost sure partial spectrum still exists just as a consequence of ergodicity. And you can ask the same question. And if you ask it, the answer will come. And so here it is. So the set of sampling functions for which the almost short pure point spectrum is empty is an energy delta set. And at this point, one should probably emphasize that the two bits that I advertised, they are about one-dimensional Schrödinger operators with ergodic potentials. So the reason is that we have now reached a point where we have a reasonably good and general theory of ergodic Schrödinger operators. With higher dimensions, we're absolutely not at that point. Okay, so there are lots of works on the random case. There are some works on the almost periodic case, but by far not as many as on the one-dimensional case. But as far as the general theory goes, there's almost nothing really. So I think the time is not right to write a book about higher dimensional ergodic Schrödinger operators. But given that, I think this is really the first general result that's interesting. I mean, that really applies to all classes, or all base dynamics at least, and then for generic sampling functions, to a large general class of multi-dimensional ergodic Schrödinger operators. Yes? Okay, so
could you repeat the question?
So the question, okay, so there is this theorem here, and the question is if you replace PP by AC, whether that's a statement that is likely true or expected to be true. So the honest answer is I really don't know. So okay, so the first thing to say, but I've said it already, the methods used in one dimensions absolutely have no counterpart in higher dimensions. The other thing that you should say is that if you increase dimension, you're more likely to be absolutely continuous than if you are in small dimension. So there should be a stronger tendency to have presence of AC spectrum. So in that sense, there's no really any reason to expect it. So no methods, no reason to expect the result. Plus, I really don't know. Right? I think that's the almost honest answer I can give. I wouldn't even bet money on either case. So. Okay. All right. Okay, so that's the first result I wanted to mention. I hope I will get to the second, maybe I won't. Okay, so I will briefly talk about, so like I said before, I mean, for the longest time, it was absolutely unclear what to do. So here, what happened is actually quite interesting. So the result is, okay, so you have a base dynamical system, and it generates operators in ZD. And you claim that for many sampling functions, you have no point spectrum. Okay. So there really are no good methods to exclude point spectrum or to study the point spectrum in higher dimensions, especially in this general context. There are absolutely no methods. So the starting point to even get a grip on what you're dealing with is to pass to finite volume. Because if you pass to finite volume, you're dealing with finite Hermitian matrices, and they have eigenvalues and eigenvectors. And I'm telling you something that you know, and how could that ever be useful? But the thing is, you want to show that there's no point spectrum, so there is some delocalization going on, and you need to formalize delocalization properties in finite dimension that apply to situations where you have eigenvalues and eigenvectors. So how can eigenvectors be delocalized? Many ways. So you have to pick one and ask if it's useful. Okay. So I will explain what kind of delocalization question you want to ask in finite volume. Okay. So you need to formulate a delocalization problem in finite volume, and I will do that. So that's the one aspect of the proof that I'll actually explain. Okay. So then you have a goal in finite volume, and you ask, can you do it? And here comes again another very honest answer. We couldn't. It's crazy. So, I mean, now at least you know what you're after, but still it doesn't help you because you can't do it. Okay? So what we were able to do in finite volume is to prove weak delocalization features, but they were not good enough. Okay? Okay, so then the next question was, okay, how did we actually get these weak delocalization features? So there was a method. And it's based on the Feynman-Hellman theorem, so something very basic. And so then the next step was to, okay, take this mechanism that gives some form of delocalization, but not a very strong form, and take this mechanism and now send the volume to infinity to get an infinite volume analog of the method. Right? You don't get a result in finite volume, but you get a method, and that you send to infinite volume. And so this produces objects that you can study in infinite volume that weren't present before. So we sort of generated new objects that are associated with the infinite volume problem that really are sort of natural infinite volume limits of something that you look at if you study the problem in finite volume. So now you have a method in infinite volume. You're looking at quantities that weren't there before. And if you look at those quantities, all of a sudden you can do it. Okay? So you have this new mechanism in infinite volume, a delocalization mechanism, and that you can actually use to prove the theorem as formulated on the previous slide. And then interestingly, from the infinite volume result, you can go back to finite volume, and you can actually prove the strong delocalization result in finite volume via the first law correspondence principle. So this is sort of the sequence of steps. I think I will only explain the first step, but even that I may not, because I do want to state the other result. Okay, so I will maybe pause and ask if there are questions. The plan for the rest of the talk is to spend a few minutes on step number 1 and then explain the second result. Okay, so you take a finite box in d dimensions, so it's 1 through n to the dth power. And you look at the restriction of the Schrödinger operator, or you just look at a potential on this box and write down the Schrödinger operator. Okay, of course you can take an infinite volume and restrict, or you just define one on the box with some suitable self-adjoint boundary conditions. So in the proof, we work with both Dirichlet and periodic boundary conditions. Okay, so here's the localization measure that we want to consider. So this is the spectral measure corresponding to this, which is an n to the d by n to the d matrix. So this is my operator, and the vector delta 1. Delta n, where n is in the box. Okay, so this is the spectral measure corresponding to this operator, this vector. And I ask what its weight at energy E is. And of course, these numbers are 0 outside the set of eigenvalues of the operator, which are finitely many. So while this is a sum over all e's, it's really a finite sum. It runs only over the eigenvalues. Okay, so you look at the squares of the weights of the spectral measures of the delta n's on its support. And that you now average over n. That's what you do. Okay. So what you can show, this is not difficult, is that if you take an orthonormal basis of eigenvectors of your operator HV and look at the fourth power of the L4 norm, so the sum of the absolute values to the fourth of these L2 normalized eigenvectors, then the average over the index of this basis is less than or equal my amount of localization that I have. And in fact, if I have simple spectrum, it's equal. So there are two ways of thinking about the quantity. One is in terms of the squares of the weights of the spectrum measures, averaged over n, and one is the fourth powers of the L2 normalized, of the L4 norms of the L2 normalized eigenvectors averaged over the index. Two different ways of viewing the same thing. Just multiplicity one eigenvalues. Okay, so if L and B is small, there are two interpretations. Either, well, because these spectral measures are again sort of L1 normalized, and I look at L and second powers of these guys, or I look at L2 normalized quantities and look at fourth powers. So something is small, that just really means that it's sort of spread out. Okay, so either if L is B is small, it means that the spectral measures have light atoms, small weights. Or the other interpretation is that most eigenfunctions, because you're taking the average here, have small L4 norms. So those are the two interpretations that you can attach to a small amount of localization measured by this L of B. Okay, so this is actually, so this fourth power of the L4 norm is often called the inverse participation ratio. You can show that for these L2 normalized guys, the inverse participation ratio must lie between n to the minus dn1. And so that's exactly the interpretation. So it's 1 over the number of sites that participate in the support of the eigenfunction, right? That's somewhere between 1 and n to the d. And so that's a quantity that's sometimes considered. Okay, and so here's the finite volume result. And as I said before, the result as stated here in our paper is actually deduced from the infinite volume result. And the infinite volume result is proved using a method that's the infinite volume degeneration of something that you would try if you had to prove the statement directly. Okay, and so the statement is the following. So for every r, which is a bound on the potential, and epsilon, which both means you can perturb by that much, and you aim for at most this much localization. So given these two parameters, for a sufficiently large n, you can perturb any potential with this bound on its size by no more than epsilon to make the localization amount less than epsilon. Okay, so you can delocalize in this sense finite dimension, sorry, the box Schrödinger operation. Okay. Good. So I should pause for 2 seconds and then move to the next result, because at least I want to mention the result. So think all the way back to the beginning of the talk, where I wrote down Simon's Wonderland theorem. Okay, so Simon's Wonderland theorem in the form given to you says that you consider these bound potentials with R being a bound. In the product topology, single continuous spectrum is generic there. That's what it says. But put this way, if you're asking what the generic spectral type for bounded potentials is, well, there's a space for that, right? If you're interested in bounded potentials, you must think of the space L infinity of Z. That's your space of bounded potentials. Obviously, it has a different topology, but it's definitely a relevant space of bounded potentials. Okay, so let's ask the question. Okay, so let's ask, well, if I look at potentials, the real valued ones, of course, in L infinity of Z, what can I say? I may be interested in the generic spectral type. Okay, so that's my question. Okay, so any guesses? What's the generic spectral type in L infinity? Okay.
L infinity is such a horrible thing if you think of it as a Banach space instead of a von Neumann space. So,
okay.
Well, should I think of L infinity here as a von Neumann algebra or as a Banach space?
Banach space.
Okay, I'm going to guess whatever the uglier answer is.
What is the uglier?
I don't know.
Okay. No, I mean, the 3 basic spectral types are pure point singular continuous and absolute continuous. Okay, so yeah, so you're right. I mean, it should be ugly, it should be different from what you expect, and it's unlikely to be AC. That cannot be generic.
No.
Okay, so then, okay, so here you go. So you guessed the correct answer. So the answer is that Anderson localization is generic. Okay, so pure point spectrum with exponentially decaying eigenfunction occurs for a generic set of bounded potentials. Now the topology being the one from L infinity. And so what I want to emphasize is the following. So, so the Wonderland theorem and then really many follow-up works basically said, and of course, I mean, okay, so I should have emphasized that before. Like if you have something that's generic and something else that's generic, then them happening at the same time is generic as well, because the intersection of 2 density deltas is. So in particular, if you have something and something that's absolutely incompatible with it, the intersection cannot be a density delta, it must be empty. So it's impossible in any setting for singular continuous spectrum to be generic and point spectrum to be generic. They can both be generic because they cannot happen at the same time. Okay, so because of that, and because of all the follow-up works to the Simon's 95 paper, I mean, whenever something is generic, it was singular continuous. Really, this is the first time that you have sort of a class of objects. Of course, if you look at finite dimensional matrices, probably pure point spectrum is generic. I'm kidding, right? But so if you have a situation where all spectral types are possible, this is the first time that pure point spectrum is generic. So in that sense, it's surprising, but of course, as you said, it has to be ugly, it has to be different. Okay, so there you go. So anyway, this is the result. So stated like this, it's surprising. But let me lift the veil a little bit with the remaining. I still have maybe 2 or 3 minutes. So I can give you a formulation of the result or a formulation of the theorem which implies that, which makes it less mysterious. So really what happens in the proof is we have a mechanism that pushes all weight of the spectral measure away from the essential spectrum so that it's fully supported in the discrete spectrum. Because when you do that, Well, the elements of the discrete spectrum are eigenvalues, so if you're supported by eigenvalues, and it's known that the eigenfunctions corresponding to discrete eigenvalues are exponentially decaying. So once you can show this theorem here, it implies the previous theorem. Okay, so if generically all the spectral measure lives on the discrete spectrum, it implies that you have Anderson localization in that sense. And then, of course, again, I'm trying to be honest, Anderson localization sort of is thought of as partly as eigenvalues being dense, so it's dense few-point spectrum. I mean, that's not exactly what happens here, although it does, of course, because the essential spectrum is there because it's the limit points of the eigenvalues. In that sense, it's still dense. But still, I mean, this is slightly less shocking, and this is actually what the proof gives, but it's not a lie. The previous result is true as stated. Okay, but this is actually what we prove. Okay, so now I'll ask you 1, 2, or 0 minutes. 2 minutes. Okay, so let me just talk a little bit about the proof here. Okay, so we should say this. Okay, so we want generically to have 0 weight on the essential spectrum. That's our goal. And of course, in all these Sanchi delta proofs, you are allowed 1 countable intersection. So what we're intersecting over is having weight bound by 1 over n. Once we intersect over that, we get 0. Okay, so we allow ourselves a little bit of weight on the essential spectrum. Okay, so then the other thing is that the map from L infinity to the weight of the essential spectrum is upper semi-continuous. That follows from general principle. And that tells you that the V's for which this weight is strictly less than epsilon, this is a formulation of upper semi-continuity, is open. Okay? So all you need to show is that these sets are dense. You know that they're open, and then you intersect with epsilons of the form 1 over n. This is how it goes. Okay, so you want to show that where your less than epsilon is open. Okay, so now you don't have to read this, I just want to flash. So there is a recent result. So sometimes you say you stand on the shoulders of giants. So this is a major work. This is due to Wodecki and Fletzer. And this is instrumental. So without that, we couldn't prove our theorem. And so what they prove is, I mentioned before already that random potentials have Anderson localization, pure point spectrum with exponential decaying eigenfunctions. So what they prove is a non-stationary version of that. Specifically, it means if you take any bound potential, and then you can look at an arbitrarily small random perturbation of that, which localizes the system. Okay, so that's localization of the background potential. And so this was sort of known due to Kunsaya from the 80s, but with the uniform distribution. But here we need it with the Bernoulli distribution, and that is absolutely new. So it's Bernoulli Anderson localization, one dimension with background potential. That's what it is. That's a recent work, and that's what we're using in our proof. Okay, so we're perturbing an L infinity, and the first step of the perturbation localizes the system, so you have pure point spectrum. Okay, and so we want to show that up to an epsilon, after another perturbation, all the weight is away from the essential spectrum. So what we do is, now that we have pure point spectrum, we select finitely many eigenvalues among this dense set of eigenvalues, whose complement has weight less than epsilon. Okay, so these eigenvalues now carry at least 1 minus epsilon of the weight. Okay, and so what we do in our proof is we turn these eigenvalues, which we fix, into elements of the discrete spectrum of the perturbed model. So we perturb so that we keep the eigenvalues, but make them discrete. And we don't change the eigenfunctions much, which also doesn't change the weights much, so we're still bigger than 1 minus epsilon. And that's the proof. And so I am not giving any details here. But again, there's this word again, uniform hyperbolicity. So in dynamics, uniform hyperbolicity plays an important role. There is a deterministic version of that, which you can use to characterize the discrete spectrum. And so what we do in our perturbation is to sort of generate this uniform hyperbolicity property, which then tells us that after perturbing, we're dealing with discrete eigenvalues that still carry weight at least 1 minus epsilon, which finishes the proof. Thank you very much.
So thank you for an absolutely wonderful talk. As somebody, I was not familiar with this Wonderland theorem, but it was because of that, it was quite an emotional roller coaster, seeing how it works, and when the proof of making things larger and then taking the intersection was very, very interesting.
Thank
So
you.
I will open the floor for questions if there are any. I'm not sure who asked first. I think.
What's known in the continuous case?
Okay.
The question was, what is known in the continuous case?
Yes. Okay. So the new work that I presented is new, and so we haven't looked at the continuum case, and I think it's not clear. I think it's not a straightforward extension. I don't have a reason to suspect that the result wouldn't hold, but I mean, in order to prove it, I think there's some serious work required. For the old result, this in one dimension generic absence of AC spectrum, that has been worked out, but several years later, but that exists in the continuum case. But for the two new results, I think one would have to invest a little bit of time.
So I would like to ask about the one lemma you showed, or maybe theorem about the L4 norm. This theorem down there. I mean, wouldn't that say that you always find a W which is drives it more to the continuous spectrum situation?
Yes,
but then on the next slide,
no. Okay, so but the theorem holds because the infinite volume result holds. Okay, so it is true, if you had this theorem, you could derive the infinite volume result, but that's not how our proof goes. So yeah, so we prove continuous spectrum, and from that we derive that the eigenfunctions can't stay all localized. I don't know, sorry, I didn't let you finish your question, but I was trying to anticipate what the question was.
Not very precise.
No, but the two phenomena are absolutely related. So this definitely is sort of the finite volume signature of continuous spectrum in the infinite volume. Thanks.
Then I ask first the simple question on the last result. If you change the topology to L infinity topology in the d-dimensional case, does that result hold as well?
Okay, so
genericity of pure
right. So here, I mean, I said I see no reason that it doesn't hold, but it doesn't mean I can prove it on the spot. Here, I think it's unlikely because, so like I said, we really rely heavily on this result, and this is just known to not have a multi-dimensional element. Okay, so in 2 dimensions, there's still hope that someone can prove localization to all energies, but it's not known. But in 3 dimensions, it's very strongly expected that you may have delocalization for small randomness, and this is small randomness here. So because this R is small in the application, because R is bound by the perturbation that you allow, so it's less than epsilon. Yeah, so if you have small random potentials in dimension 3 and higher, the big conjecture is that you have AC spectrum. So you definitely don't have these eigenfunctions that you can work with. So again, it's not that I could disprove that the theorem extends, but there's absolutely no reason, and really a strong reason, to expect that it won't extend.
I wanted to ask, you were mentioning the application of the Feynman-Hellman theorem. Can you outline this a bit? Where it
yes, so okay, thank you for the question. Where am I? I'm trying to... Okay. Where are we? Okay, anyway, so we were talking about these L4 norms, right? Okay, very good. So, so localized eigenfunctions have most of their weight in a very small region, so where the inverse participation ratio is close to 1. So there are a few sites that carry much of the L2 mass, whereas extended eigenfunctions are more spread out in space. Okay, so the Feynman-Hellman theorem tells you that if you perturb at a certain site the potential, then the eigenvalue will roughly move according to the expectation, according to the eigenfunction. So if the eigenfunction is an idealized, a perturbation of the delta function at that point, that means there's a very large velocity with which the eigenvalue moves if the eigenfunction is very heavily concentrated there. Okay, so the Feynman-Hellman theorem tells you the larger the eigenfunction is at the site where you perturb, the faster the eigenvalue moves. Okay. And so the thing is, if you have too many localized eigenvectors, actually the localization centers have to be spread out in space by orthogonality of the eigenvectors. So the localization centers have to be really nicely spread out in space. And if many of them are very localized, then you have lots of movement of eigenvalues. And actually, you can tune them so that the eigenvalues move maybe, okay, so eigenvalues are in R, so they move either this way or that way. And then you know that in one dimension, okay, we're in high dimensions, I'll tell you in a moment how that works. In one dimension, you know that the eigenvalues are always simple. So if you start with a situation where you have the eigenvalues located in whatever way you want, but then they move with large speed, and if you have lots of eigenvalues, the spectrum for all sizes n will always be in the same compact interval from minus 2d minus infinity norm of v and plus 2d. Anyway, so you are in the fixed compact interval in which you have more and more eigenvalues, and then they start to move in opposite direction, and then they collide. That's sort of the contradiction. So if you have too many eigenvalues, by the Feynman-Hellman theorem, that will lead to collisions of eigenvalues, which is a contradiction because you already know that eigenvalues must remain simple. Okay, so that's an oversimplification. What we use is, well, if eigenvalues move, then they bunch up, and the integrated density of states becomes very steep. But you have global regularity results for the integrated density of states, which prevents eigenvalues from bunching up. So it's the same principle. So if you have too much localization, eigenvalues can be directed to very small regions, which makes the IDS more irregular than it can be. Does that answer your question? Okay.
Maybe we have time for one more question. Well, I was actually interested in this continuous case because it seems like countability is such an inherent part of the arguments that you're using. And you said that the theorem has been worked out in one dimension for
only the 2005 theorem. That has
yes. Okay. I was referring to that theorem.
Okay.
But I'm wondering, the techniques must be very different, or are they still rescuing something from this idea?
No. So it's exactly this Lyapunov exponent stuff which I refer to. So here, so this is the result that has a multidimensional analog, and it's really about showing that the Lyapunov exponent is strictly positive for Lebesgue almost every e, and this comes from Kotani theory. So
when I talk about the continuous case, I'm thinking about where the Hilbert space is L2 of R instead of L2 of Z.
Exactly.
Yeah, okay.
And so what is used here is so-called Kotani theory, and that exists both in the L2 of Z case and in the capital L2 of R case.
Okay.
In the L2 of R case, it's just more difficult to implement, but once you know that the basic theory that underlies the argument exists, it's no longer surprising that you can use it. But to use it, you have to work a little harder, but the result is in the end the same.
Okay. Well, thank you so much. I think that's about all the time we have, but it was a very nice talk. Thank you so much.
Thank you.
We even say